Hello, everyone. Thanks for joining the sixth episode of our Power Hour webinar series, or the first one of 2026, where we're going to be looking at power quality and the impact that it has on your electrical networks in terms of reliability and electrical safety. For those that don't know me, I'm Daniel Henderson. I'm a chartered electrical engineer based in the UK. I'm the global head of electrical safety and partnerships for Scanware. And hopefully I've met enough of you on the past webinars. I'm joined today by two power quality engineers. So I'm joined by Steve Young and Tony Parsons. I'll now pass you over to them to introduce themselves so you know who's talking to you today. And I'll pass you over to Steve.
Yeah, hi everyone. I'm Steve Young. I'm a independent power quality engineer based in the UK. For the past 25 years of my 35-year career, I've been engaged in different kinds of power quality studies, covering many different sectors and applications. In that time, hopefully, I've gathered some useful information, and I'm very grateful today to have been invited in and share some of that experience with you all, along with my co-hosts, Dan and Tony.
Yeah, and over to me, I guess, is Tony Parsons. I'm with Eaton in the U.S., located in Austin, Texas. Just a quick word about Eaton to begin with. An international company. The part that I work in deals primarily with power distribution and control, and I think we're well known in that sector. We have a history dating back all the way to the Westinghouse company. But not dwelling on the other things here, but just a slide to show you some of the other areas that we are involved in as well. So, a number of different things. About me personally, I am an advisory engineer with Eaton's Field Services division in the U.S. I've got 26 years and counting of experience in the industry. Started out as a power quality engineer and have continuously had the opportunity to add other things to I guess the resume, if you will, but still quite involved with power quality and harmonics. And like Steve said, excited to have the opportunity to share some of that experience here with you today.
Thanks both. So just a bit of housekeeping. Everyone that's registered will receive the slides after the webinar via email, and you'll get a recording sent as well. Post-webinar, please fill in the survey. Let us know how we did and anything you want to do differently. So we'll go through the topics that are coming up. You'll see them there, but they're not set in stone. So if you want to see something different, let us know, and then we can look to possibly revise that if there's enough of a want. Make use of the Q&A throughout. We will have periods when we can do question and answers. And if you want to be registered for future events, let us know in the chat and we can make that happen. So this is the overview for 2026. Today, we're looking at electrical safety and reliability, looking at power quality and the impact on electrical networks. And again, I've picked this because it's a topic that often gets overlooked. I've not really seen many webinars done on it in regards to reliability and electrical safety. And in my past roles, when I've been an electrical duty holder or responsible person managing electrical networks, I've been impacted by this through lots of different ways, definitely in terms of business continuity and electrical safety. So I think it's a pertinent thing to bring to the table and something that probably doesn't get discussed enough. And there's a bit of an overview of everything else that's going to be happening this year. But again, if you think something different is more pertinent to you on the call, let us know and then we can maybe look to modify that. So learning objectives, hopefully these are what we're going to cover throughout. I think it'll probably go a bit further in a depth in some of the areas, but this is the basis of what we want to look at throughout the webinar today. And I'll pass you over to Steve to start us off.
Yeah, well, poor power quality, experience tells us, can cause chaos, not only to the connected loads, but also to the electrical networks to which they're connected. A study that was undertaken by Leonardo Energy back in 2008 revealed that some 150 billion euros per annum is the estimated cost of poor power quality to industry and commerce in the EU. And interestingly, less than 5% of that figure was estimated to be spent on mitigation measures. Now, similarly, in the US, the Electric Power Research Institute carried out a similar study, estimating that that cost was in the region of $188 billion per annum. Now, these studies provide important information relating to the root causes of those problems, which Tony's going to tell us a bit more about.
Yeah, EPRI, the Electric Power Research Institute, also did a study where they surveyed a number of different customers across different industries in the US to get an idea of the types of power quality issues that were causing problems. As you can see by this chart here, kind of the heavyweight champion, if you will, was a voltage sag, but there are many other disturbances as well that come in: swells, switching transients, power system harmonics, high frequency noise on the line, different things that we show there. We're going to cover several of these categories here today, some of the important ones, and not only tell you about what the impacts they can have, but also tell you about some solutions that you can use to try and mitigate these disturbances in your system.
So why do we conduct a power quality study? Well, there's really two main reasons for that. Sometimes when our phone rings and it's post-incident, so we're undertaking, if you like, a root cause analysis, trying to work out what's happened. I think, though, with increasing clarity now, power quality engineers and facility operators alike are recognizing now the benefits of proactive monitoring. Now, that can identify really useful characteristics like true loading and spare capacity, but also identify existing hazards and emerging risks on the network as well. Now, we learned about the heavyweight champion, if you like, in that voltage sags are probably the most troublesome characteristic that we have to deal with. So if you look at these characteristics there, we've got time along the horizontal axis, and we've got magnitude on the vertical axis. So by measuring both the magnitude and duration, and perhaps cross-referencing that with the low limit that's tolerated by the connected loads, we know that the magnitude and duration define then the impact on the equipment.
So I suppose just a quick poll. Has anybody on the call got any power quality issues on your electrical network? I thought it's a good question to ask, especially just after we cover probably the biggest hitter of them, it being voltage sags or voltage dips. And I ask because again, in a previous facility that I was the engineering manager of, looking at this, they had, I don't know, 10 production lines approximately, each operating in their own silo of production. And when asked individually, have you got any power quality issues? No, nothing really, nothing. Then when you start looking at it, you see they're on the under voltage side, on the low level, and then you start looking at when they've had issues on we have an under voltage trip maybe every 2 weeks, but it's only off for an hour or every 2 hours, or 2 hours, something like that. But you're talking $10,000 per hour worth of production, and every production line had the same. So again, every 2 weeks, you're talking around sort of $100,000 to $200,000 of lost production, plus the impact and the downtime. So it's again just a question, just to see what that looks like. So yeah, it's good. It's good. Thanks for your inputs on that. Bit of a mix there.
Yes, slight error on the last part as well. It should be not sure, not sure.
Sure, I've got them. No, it's it's good. Good to see that people haven't got any. Be good to know what backs that up, whether you've had studies done or whether you're actually looking at your network consistently.
So the Information Technology Industry Council produced this curve, and the curve's really useful. It defines the tolerance limits for connected equipment, and it uses duration on one axis and magnitude on the other, just to explain. So generally then, events that are inside the envelope are typically tolerated, they're okay, but events outside of the envelope are going to increase the risk of problems, trips, resets, etc. So if we've got, if you like, events that are above the curve, then we potentially have an unsafe operation. And below the curve may result in automatic disconnection and increased disruption of the supply. So we need to understand what we can do about that.
Yeah, so as far as solutions go, several things that you can do, and really, to reiterate the need for doing a power quality study, and we'll talk more about measurements later in the presentation, but a study to characterize magnitudes and durations of voltage disturbances you may be exposed to can help you determine what type of solution is really most applicable. For voltage sags, there could be voltage conditioning equipment that can, that can help. Different trade names there, sag fighters and sag ride through modules and things like this, that may be good for example, single phase voltage sags, but not as good for three phase, not as good for total interruptions. If you're trying to protect against a total loss of voltage, you may have to go to something like a UPS, uninterruptible power supply. The picture on the right-hand side shows an example of batteries backing up a UPS in a corporate data center here in the US. Just gives you an idea of the amount of energy storage that may be needed. But the idea being that if the utility power goes out of spec, then let's bring in some of that stored energy to help make up the difference. Of course, that only gets you so far. And so if you're looking at potential extended outages, you may have to go to standby generation, right? Great during outages, but what do you do in the several seconds that it takes for that to come online? And I guess last one there with things like AI loads. One of the things that's receiving a lot of attention in the US now is AI data centers that have wide and fast load swings that can cause voltage variations in the facilities. They're looking at things like supercapacitor backed energy storage to potentially help mitigate those types of disturbances. So as the system changes, the solutions have to change as well. With each of these solutions, there are pros and cons, and we're not going to go through and dwell on every single thing here, but just the idea, for example, the UPS is great for protection of electronic loads. What are some of the drawbacks? If you're feeding loads that draw inrush current, like motors or transformers, they may have some limitations. You may have to upsize them significantly, which increases the expense, potentially increases the footprint. And then, maybe you have to deal with batteries that you didn't have in your system before. So again, footprint for that, but also potentially introducing additional hazards that you didn't have to worry about before you had those in the system. So with all of the solutions, again, trying to characterize the environment in your system so that you can choose the correct one, really the best way to go.
Yeah, and a big thing is understanding the source, isn't it? It's so like on one side that I had, a lot of the transformers, the tap positions were quite low, or high on the HV, low on the LV side. So and again, that had been done many moons ago for energy saving initiatives, but the load changes had changed on the end. So those variable frequency drives that were now on, that they were close to their minus 10% under voltage threshold. So as soon as you had a dip upstream on the network, either by a large load starting or something on the utility network, they dropped straight below their ride through voltage on the under voltage side, causing downtime. And again, if your supply lines, sometimes you have overhead lines, which can sometimes have auto reclose functions and things. And when we've got different weather conditions, that can be an impact if we've got no separate supplies or ride through functions like UPS and things like that. It's about understanding, I guess, whether it's on site or off site that causes the issues, which I'll now lead nicely into Steve's next point.
Yeah, thank you, Dan. It's a good point. So if we've got a voltage dip, we need to try and understand a bit more about where it comes from. So through applying good measurement and analytics of that data, we can analyze inrush currents, short duration currents, and potentially tie them back in through data analysis to the voltage dip event. So for instance, if we have a automatic operation of a large induction motor, that can create an inrush current, and of course, in an Ohm's law relationship, they will go across the transformer and create a voltage dip at the same time. So that's a automatic system actuation, if you like. But similarly, it could be a manual operation, a manual switching that creates that inrush current event on the network. So if we get an inrush like that, we've got another consideration as well. It may result in the automatic tripping or automatic disconnection, if you like, of an overload protection. So to understand a bit more about that, we look at an inverse time curve. Now we can populate that with some values. Here, if we use an example of IN across which is the design current across the horizontal axis, and populate that with let's say it's a 1000 amp overload protection. That means the design current is 1000. Then we can look at the curve and look where we've got the red arrows. If we have a 6 times that value, okay, 6000 amps, then it's not going to trip at 0.7 of a second. It's right on the curve. So we can pose a question to you within the poll now. In an instance where we have a 6000 amp event of magnitude of 6000 amps, but an extended duration of 1 second, should the overload protection device automatically disconnect? And that's your poll question.
It's a bit of a callback really to the electrical coordination and protection and fault levels webinar we did in November. So hopefully we talked through the inverse curve and trip characteristics. So hopefully most people on the call answer this correctly.
I'll give it a few more seconds.
No worries if not. Obviously, some people might not be on. Some people might not be their bag.
I'll give it 5, 4, 3. Right, stopping the poll now.
Excellent. Yeah.
Majority say yes. Some no. Some not sure.
Okay.
It's good, isn't it? Now we can do
Good.
callbacks to previous webinars.
Good. So that's correct. For any of you that answered yes, what we're saying is you can see there the extension of the curve has breached that inverse time curve, which means really we expect automatic disconnection of the overload protection.
Yeah, so as far as dealing with these inrush currents, part of it, and a big part of it, and I know Steve has seen the same things when he's done surveys, but just proper system design. You know, if you have sensitive electronic loads, don't feed those things from the same transformer as your large motor loads that may be starting several times a day and creating voltage sags, or don't feed your your PLC control equipment that controlling your whole process from the same panel that your welders are fed from, right? It's you're mixing sensitive loads and polluting loads, and just trying to get some segregation in that sense can go a long way. We talked about motor starting inrush, and so there are motor starting methods that can be used to help decrease the inrush currents. And if you decrease the current, Ohm's law says that, hey, we have less voltage drop. We're going to decrease the impact as well. Kind of the baseline, what we would call in the US FVNR, or just across the line, full voltage starting. That's the highest inrush. But maybe you could put on something like an auto transformer starter, supply a reduced voltage to the motor to get it up and running, and then switch to the full line voltage, or a soft starter, kind of a power electronic answer to that auto transformer starter. The ultimate would be the variable frequency drive or the adjustable speed drive, which really starts the motor. I don't know if gently is the right term, but you bring up the voltage and the frequency kind of together, really eliminate the inrush. With transformers, when you energize a transformer, you also have inrush current as well. It's a little harder to mitigate. We don't have like soft starters necessarily for transformers. More common, probably design around the issue and make sure things like your relay settings are set to make sure that you accommodate whatever inrush levels you may expect.
Obviously, yeah, and as you mentioned, Tony, we're not switching in transformers all the time, are we, as much as we would things like motors?
Exactly. Motors, typical motor may come on and off several times a day. Transformer, hopefully you're not doing that, right? It's kind of set it and forget it, let it run for a little while.
Yeah, perfect.
As always, potential drawbacks to consider, those reduced voltage starting methods, reduced starting torque results from the reduced voltage. So is that torque enough to actually get the load up and running? If it is, the reduced torque generally means you're going to have longer starting times. Is that going to create an issue? And then even with the VFDs, again, little no inrush current, but you're going to have additional expense for that added equipment. And then they can be a polluter of their own. They can create their own power quality problems with power system harmonics being one of the major sources of that type of disturbance. We'll come back to harmonics in just a minute, but before we get there, another voltage disturbance to kind of to close out this category, voltage transients. Steve showed you earlier that ITIC curve and talked about the envelope where we have good performance kind of in the middle. If you go below the envelope, you're in voltage sag territory. If you go above the envelope, you may be in this voltage transient realm. The idea here, the difference between a voltage transient and a voltage swell would be the duration, right? These transients, we're talking about high magnitude, but also very short duration voltage events. The graphs on the right-hand side, you can see kind of the voltage sine wave, but you see the very brief, the very high magnitude excursions from that. Those are the transients. The left-hand side, we've got impulsive transients. They kind of hit it and then they go away. On the right-hand side, one that may be more characteristic of switching a capacitor bank online. We have some oscillation. We call that an oscillatory transient, and it can result in extra zero crossings of the voltage. We go across the zero axis. Sometimes control equipment uses those zero crossings as a reference, and so you can actually kind of foul up the controls with this in some ways. But if the transients, basically, if someone talks about spikes or surges on the network, this is what they are talking about. So how do we fix these? I guess where do they come from? First of all, they can be both external and internal. External, maybe lightning strikes on the system, capacitor switching on the utility system, or faults on their network. Internal, some of the same things, right? But also including the operation of the load equipment in the facility. We already mentioned welding. That can be another source. The transients can be problematic in a couple of ways. The high magnitudes of the voltage can directly damage insulation of load equipment, whether you're talking about on circuit boards or even motor or transformer windings in the, kind of some extreme cases. The oscillatory transients can cause misoperation even if the magnitude is not high enough to destroy anything. As far as solution methods, if we're talking about lightning, we've got special lightning abatement systems that we can design and deploy. The picture on the right-hand side shows, you can see up at the top of the structure, some lightning rods or strike termination devices for those. That's a 138 kV transmission tower, but you see those on buildings and other installations as well. Inside the building, surge protected devices or surge arresters. But with all of these things, what they're trying to do is to provide an alternate path for that high energy to travel. Ultimately, what we want to do, instead of letting it go and affect our equipment in the building, we want to give a path for that energy to go to ground or go to earth. And so the grounding and bonding or the earthing system is an important part of your transient mitigation. People sometimes overlook that, but if you don't have that low impedance path for that energy to travel, then you're going to increase the likelihood that you're going to have problems with the equipment that you want to protect. And to that end, next slide shows probably the biggest problem that I see on low voltage surge protection, and that is the effective lead length. The picture on the right-hand side shows what would be called an integrated or an integral surge protected device. We have a low voltage surge protected device mounted right on the panels or the bus bars inside a panel board. That's the best thing. If you can directly connect to the terminals or the bus bars of the equipment you're trying to protect, you get the best degree of protection in that case. What if we can't mount it there? You can't always do that. And so you have a lead or a conductor going out, connecting from the panel or MCC or whatever to the to the surge protected device. You want to keep that lead length as short as possible. Again, we talked about the impedance making a difference. Well, the impedance of that lead can reduce the effectiveness of the surge protected devices. The typical recommendation, keep those leads to 18 inches or roughly half a meter or less would be the ideal case. As far as lightning protection, again, kind of a different animal altogether. There in the U.S. there is a standard NFPA 780 that deals with design and installation of lightning protection systems. In the IEC world, IEC 62305 has some similar information. The goal with this, again, to give an alternate path for that lightning to flow. three main components. We have the strike termination devices, or AKA the lightning rods. We have the grounding electrodes to connect to the actual conductive earth, and then conductors that connect number one to number two. Simple if you look at it in that way. And again, you see these things everywhere. The pictures on the right-hand side are from that I took on a family holiday when we were visiting the Leaning Tower of Pisa a couple of years back. And I just wish that I'd known at that time that I was going to do this webinar. I would have gotten a few more pictures that didn't involve my wife and kids doing selfies off the top of the tower. But you can, next time you're up there or some other, some other place, look around, see if you see those types of devices in play.
He's actually playing that down. We got to see all of his holiday pictures, and there was none of his family. It was all, vertical transformers, lightning rods, things like that. So,
well, you look for what you want to look for. I look for what I like.
You stick with it, Tony.
No, I appreciate that, Tony. Good pictures.
So on to harmonics. Harmonics is a term that we give to the impact that these modern electronic loads have, firstly on the current waveform, and then in an Ohm's law relationship, ultimately on the voltage waveform. So if we look at some of the producers of nonlinear current, typical things that we see in everyday applications now, we really can't get away from them. Most applications are predominantly harmonic nonlinear loads now. Computers and servers, office equipment, electronic lighting ballasts, probably most importantly, variable speed drives. In fact, almost anything electronic has its own harmonic signature. And the way to think about harmonics as we work through these slides are that they ultimately manifest as heat and vibration and have a significant impact on the application. So in order to understand that a little bit better, we can populate an FHL curve, a harmonic loss factor curve. This is a typical harmonic loss factor curve. Let's consider it as the only one for a distribution transformer. The red curve exists. Along the horizontal axis, we have a harmonic loss factor value, which is measured during typical peak demand by the instrument. And so up on the left-hand side, we see the transformer capacity. Let's use an example of 1000 kVA from 0% loading up to 100. So if we don't have harmonics, very little insignificant amount of harmonics on heat and vibration, then there's no need to derate significantly. So we might consider that this 1000 kVA transformer has an optimum limit of 80% without any harmonics.
Yeah, so just to, I suppose, give you a visual representation of that, this is a transformer tally plate. And when we're talking about the rating, this is the typical rating of a standard transformer measured in kVA, so 1000 kVA or 1 MVA transformer. And what Steve's saying there is if we have a standard linear load, so none of those sources that we previously discussed on the other side, then we'd look to load that up to ideally around 80% to give us that bit of headroom, we would load that to 800 kVA and give us that 200 kVA buffer in there.
So what about if we actually do have harmonics on the system? And most systems will have nowadays. So we're going to populate an example now where we have a harmonic loss factor. Remember, this is measured by the instrument during typical peak demand. And in this instance, it's an FHL value of 7. So we draw that line across and we take 80% of it. So in our example of a 1000 kVA transformer, then the safe limit of that transformer has been reduced from 1000 kVA, given the optimum limit and the consideration for harmonics, down to 40% or 400 kVA. If we breach that line, then we're now at significant risk of an exponential rise in distortion and unwanted heating and problems. Now, when we get different types of waveform distortions on the voltage, that might mean across the zero line, we might have a double crossover, which is really an unwanted characteristic particularly for electronic load-bearing equipment, and also similarly with flat topping of the waveform, depending on the type of harmonic loads that we've got connected. A lot of items will fail or maloperate, if you like, if they're supplied with this flat-topped waveform. So the less voltage distortion less current distortion we have on by way of the harmonics, the less voltage distortion we're going to have. And ultimately, remember, harmonics manifest as heat and vibration, and it can be very significant.
And it's good to see this actually in it's not good to see when you're responsible for the network.
No.
But I've had quite a few issues of this where, especially in facilities that have developed over time. So I've had one where I had two transformers sat next to each other, so sister transformers feeding one common LV switchboard. Previously, they've had a lot more linear load on each side, the one or two production lines on each side of the board with the bus coupler open. And they, again, the load difference, one had a higher FHL than the other, and the difference to physically see that was around 25 degrees C in oil temperature between the two, even though the load was theoretically the same. And so it was really good to see that. But essentially, I saw that manifesting again, starting to get faults back at the tap changer, and seeing that oil start to degrade. And one of the worst ones, the one that kept me awake at night, was this example. So this was a transformer that fed part of a process. Again, on the tally plate and on the size of the variable frequency drive that it fed, it was more than capable of supplying that load, but taking into account that FHL of 7 on this one, essentially, this was catastrophically failing around every 10 years. When I look back through the sort of history records, and I'm talking catastrophic failure. So it was a failure of the tap changer, hot oil, flashover, and you don't want to be in the vicinity of that when that fails. And the degradation of oil when it was changed after about 12 months, you'd start to see metal-to-metal thermal contact, because the typical part to fail was the tap changer. Again, common with signs of overload, where you start seeing those arcing situations going on, and this is a one that was captured early. But essentially, yeah, this is a really good example of where it hasn't been done right in the design.
Yeah, so we can skim over the impacts of the effect of high current distortion quite quickly, keeping in mind that, again, these manifest typically as heat and vibration. So just to pull out a couple of the key ones, we've learned that overheating generally and the requirement to derate transformers. We also have further consideration for interaction with capacitors, which we'll learn about in one of the upcoming slides, and also reinjection of those harmonic currents back onto the utility, which might get you into some trouble with a distribution network operator. And wherever we've got high current distortion and we've got ultimately considerations for voltage distortion, we can look at that in the context of Ohm's law. So if we think of V being the voltage distortion, the product of high current distortion, V is I times R, if you like. So across a fixed impedance of a source, if we increase the harmonic current, then we're going to increase the voltage distortion. So simplified, the more harmonic current on the supply, the greater the voltage distortion on the network. And that's going to be seen everywhere on that low voltage network. And we can see on the next slide some information and some manifestations, if you like, of typical effects of high voltage distortion. We've got even linear, this is non-harmonic load, starting to draw that distorted non-linear current, so adding heat and vibration, torque pulsation in motors almost trying to drive themselves backwards. This interaction that I alluded to with capacitors, as well as a voltage disturbance, insulation, stress, and of course, untimely failure of key items of load-bearing equipment like power supply units and electronic lighting. And of course, that list isn't exhaustive. So what can we do about it?
Yeah, there's several things, Steve. One would be equipment design, right? We can look at, we talked about VFDs a little bit already, or adjustable speed drives, if you prefer. One of the most significant sources of harmonic distortion in the system, you can use higher pulse order VFDs instead of a 6 pulse drive, a 12 pulse or 18 pulse. And not going into the technical details, but those are designed to help mitigate and reduce greatly some of the highest harmonic currents that may otherwise be injected back into the systems. One of the newer developments in the becoming more and more common in recent years, active front end VFDs doing much the same thing, or loads or equipment that have some degree of mitigation built in. Solar inverters, crypto miners, the folks out there trying to get the Bitcoin or whatever. Sometimes installations with a great deal of load, and if the manufacturers of those devices weren't trying to take harmonics into account, they really would be causing some problems for the system. Now, all of those things, they're electronic loads. They have components that are switching sometimes at very high frequencies. Steve is going to, in the next section, talk about the effect of some of those things that you see sometimes, the super harmonics that can cause other types of issues. But if we can't get rid of the harmonics with equipment design, maybe we can get rid of them with filtering. There are passive filters. We'll talk a little bit more about power factor correction in a few moments, but kind of giving you a preview. If you put capacitors in your system to help correct your power factor, you can also put an inductor in series with it to tune it and essentially make it into a harmonic filter. Typically with that, you're targeting one harmonic, that may be kind of your most problematic. But there are such things as active filters as well. And I call that the noise canceling headphone of the power system. Think about what your noise canceling headphones do, right? They've got a microphone. They're kind of listening for the ambient noise and sort of, you may not think of it this way, but they're actually injecting the opposite of that noise, right? To help cancel it out, whether you're on the airplane or the train or whatever, to try to make it a little less noisy, at least in your head. The active filter can do the same thing. Look at measure the harmonic content of your distorting loads and inject current that is out of phase with it so that it cancels and looks much cleaner to the rest of the system. I think we got, there we go. As far as dealing with, transformer heating, again, transformer selection can be important in the U.S. or, if you're dealing with, IEEE standards on your equipment. There is an IEEE C57.110, a standard that talks about how to essentially derate your transformers for harmonic loading. And I think Steve gave a reference that the rest of you may use for similar things. In the US, we also have K-rated or K-factor rated transformers. The K-factor is really very closely related to that FHL that he showed. And so essentially using transformers designed for the harmonic levels that they may see. And sometimes, again, with the transformers, using isolation transformers. Sometimes it can be used to separate the harmonic producing loads from the rest of the system. We kind of get those isolated on one transformer. We kind of design that to deal with the effects, but then the separation just caused by the impedance of the transformer itself helps the remainder of the system. Or, if we have large, I've seen it in cases where we have large rectifiers, things like that, use phase shifting transformers, one delta delta, one star delta or Y delta to produce some phase shift that helps reduce in some degree of harmonic cancellation further up in the system. So lots of things that you can do if you're dealing with these type of issues.
So on a wider range of frequencies, if we consider harmonics really being at the lower end of that, and electromagnetic fields and EMC being at the higher end of that, there's traditionally been a gap in the middle, which is now commonly and affectionately known as superharmonics. So if we look at the different types of superharmonic generating items of plant and equipment, some of the most common ones, perhaps the most common one that I see, are inverters that are on modern PV or photovoltaic farms. Same can be said for battery energy storage systems, electric vehicle charger applications. Tony referred to active front-end drives often fall into that. And obviously some other items of load-bearing equipment as well now, using higher and higher switching frequencies like modern LED lighting and even some UPS systems as well. So we need to understand a little bit more about the impact that these superharmonics have and what we can do about them. So this is an example. The black chart at the bottom, the voltage one, is a chart showing, if you like, the sinusoidal waveform before the system started on the left-hand side of the image, and then after, if you like, after the PV, the photovoltaic inverter, was switched on. You can see the feathering on the waveform that's only visible if you're using quite an advanced type of power quality instrument. So this is above harmonic, normal harmonic range. The top left-hand image shows the information from the instrument with respect to voltage. So the red line indicates the limit by way of it's IEC 61000-2-4 class 1, and we can see a significant exceedance in that value there, and that indicates the switching frequency of the inverter. Now, that's going to have one phenomenon that we call constant high frequency voltage disturbances. But as we draw current at that frequency on the right-hand side, we're going to see corresponding current drawn at that dominant frequency. And that has its own set of considerations that we can now take a quick look at. So first of all, let's concentrate on the voltage. So we know a lot of university-led papers and such like have already acknowledged that the presence of constant high-frequency components can give rise to arcing, particularly on the HV windings of the transformers. Now, as the partial discharges and micro arcs are within the tank, if you like, as those arcs are extinguished, there's a bubble that's formed that's predominantly rich traditionally in hydrogen, but also in some other dissolved gases, as we call them. Now, you can see the image on the left. There's some tiny little bubbles there. And these systems have often fitted with automated Buchholz relays, which will take the transformer completely out of circuit if that becomes unsafe. Now, wherever we've got high levels of voltage distortion, remember, we're going to start leading into high levels of current drawn at a similar frequency.
Yeah, it's really interesting actually, because in other industries and other fields, typically when we're doing our oil analysis, when you get, obviously you do your DGA analysis, but you don't often see, from what I've seen especially in the PV or the solar industry, you get a high amount of gassing in the transformer, so high amounts of DGA, and it's not something that. And I've seen it where, it's just an accepted thing, because obviously you've got these micro arcs and PD because of the nature of the inverters and then the impact on the network. But it's something that you would never accept in other parts of industry, sort of in standard distribution or, any other manufacturing, as an example. The types of loads, you wouldn't tend to see this. And normally your protection, like you say, where it either hasn't got a conservator, and you're doing your standard DGA and you've got temperature and overpressure protection, or where you've got or where you have got a Buchholz relay, that's really there for oil leaks or significant event like a major arc inside your transformer. Then you get the bubble going, up to your conservator and tripping your Buchholz relay. And on smaller transformers, you might have an integrated dissolved gas and pressure, temperature transducer, which looks at this. And again, it's so common that these do trip on solar sites.
Very common.
And it's the accepted thing because of the nature of the network, which is, I just find it interesting because it's not the accepted norm as an electrical engineer from other industries, which is it's quite just find it quite interesting.
And so we need to understand a bit more about the impact of these superharmonic components. So if we look at the impact then on the voltage ultimately has on the current, we can look at the skin effect. So frequency is proportional to skin depth. All that means in simple terms is the higher the frequency, the less depth that component can flow within the conductor. So that's going to lead to overheating. It can lead to further breakdown of the insulation, again leading to further dissolved gases within the tank. And ultimately, as we're breaking down insulation, no surprise, this can sometimes manifest as catastrophic failure. So looking at power factor then is another consideration. And I always think that the fiscal bills really are a very useful start with power factor. The fiscal bills will tell us if we're getting charged with what we call reactive power charges. So just to explain where they come from, if we've got an induction motor on site, physics dictates that we will need to import reactive power to magnetize the motor and make it spin. So we need the through, the kVAR, to make the motor work. Okay. Now, if we have a lot of induction motors, then we've got more reactive power. So we may see a reactive power charge appear on the bill as the power factor drops below the prerequisite level, which is usually about 0.95 lagging, as we call it. So we can show this by way of a pint analogy. So if we look at the useful part of the drink, which is the beer, that's the kilowatts, and it's common to both pint pots. On the left-hand side, we have an uncorrected power factor. So we've got a lot of froth on the left-hand side there because we're drawing all of that reactive power from the grid. And of course, the summation of those two things is the apparent power, the kVA. And we're also charged by apparent power on the bill as available service capacity. So there's another charge associated with that. The pint on the right-hand side is with a corrected power factor, and that is through mitigation. That's through using a power factor correction unit to supply reactive power, or VARs if you like, so that we don't have to draw it from the grid. And consequently, that can have a payback, if you like. But we must be very careful in the selection of that equipment to make sure that we don't get a technical conflict.
The old pint pot analogy.
We like the pint pot analogy.
We do.
So the image here and the little notes above really are pointing at the very real risk of technical conflict. I saw 4 of these across a 12-month period. Obviously not while I was there, fortunately, but you get called in to investigate. We talked about post-incident root cause analysis, if you like. Very common to have a technical conflict between harmonic generating loads on site and unprotected capacitors. And unfortunately, whilst there are systems in place that should hopefully let these things trip automatically and safely, it really isn't always the case. So we need to consider mitigation, which Tony's going to talk to us about, and what we can do about that.
I've seen 3 of these as well. 2 of them, it just resulted in the capacitor banks failing and then the equipment going offline.
Yeah.
One ended up in a fire, which obviously isn't ideal from a safety perspective or a reliability perspective.
No.
Yeah, and as far as mitigation of power factor, like we kind of hinted at on the last slide, the most common means of correcting your power factor is to apply capacitors in your system. The capacitors supply some of that reactive power locally rather than getting it from the utility. So you increase the power factor in the facility. Maybe you decrease the losses because we're drawing in less current from the utility. The goal in any case would be to save on energy charges and or demand charges from the utility. And in the best cases, I mean, the payback period can be pretty quick. I mean, you can talk about even less than a year in the best cases. Capacitors can be either fixed or switched. Fixed, you turn them on and there they are. The switched may have automatic means to switch different stages in and out, and that can help if you have widely varying load levels in your facility. Generally you don't want to overcorrect when load is light, maybe at night or overnight or on the weekends or whatever. And so if you can bring in more capacitance when you need it and switch it out when it's not needed, that can be a help. The capacitors are typically available either at low voltage or medium voltage. Sometimes they're installed with large motors. Large motors may not have the best power factor, and so in order to keep from correcting when the motor's not on, we switch the capacitor with the motor. Common, at least in some industries. But as we just saw, and we saw the aftermath on the last slide, the big warning: capacitors can exacerbate harmonic issues if there are nonlinear loads present. And so application of power factor correction capacitors is not just as simple as looking at your bill, figuring out how much kVAR you're using, and then selecting something out of the catalog, right? We really needs a little bit further analysis to make sure that you're applying the right type of equipment in your system.
Yeah, just quickly on the standards, I won't spend too long on this one. We talk about voltage distortion quite a lot through this presentation. I just wanted to point out that good practice generally accepted by power quality engineers is 5% THD being a limit. So we can take that forward into our reporting and analytics. So traditional monitoring, we just populate, if you like, a consumer's high voltage or medium voltage ring with 3 transformers transforming down to our usable low voltage. Typically, a portable power quality analyzer would be connected directly downstream of that transformer so that we can pick up all of the associated characteristics and values across a typical peak demand period. They're quite commonly 7 days, sometimes a little longer, depending on the specific requirements. So once we've got that, reports can follow all different kinds of formats, but hopefully they're going to tip their hat to some of the things that we've learned about in today's presentation. Of course, kVA demand, but also harmonic content. For instance, the left-hand bar chart here shows the loading versus the transformer optimum limit without any consideration for harmonics. But the right-hand side one shows it with due consideration to that harmonic loss factor. And ultimately, because we've gone over where we should be, the voltage distortion value has gone over the 5% recommended limit, and we're getting up towards 8%. And useful reporting like this can give us some very valuable insights on what we can do about it and the spare capacity that we can regain. Similarly, we can pick up short duration events like this one. So we've got particularly if we have permanent monitoring, this is particularly useful. And this is something that is available now with the likes of the remote power quality system, which is very clever in the way that it picks up 10 millisecond events constantly, raising alarms. And this gives us the ability to capture events and associated inrush currents at very, very fast occurrence rates, and we're able then to provide useful information back to facility operators.
Perfect. So no, that's really good. I think it's a good point to bring us to this to review the takeaways. So power quality disturbances are real and present, but they are measurable and they are repeatable, and each one produces operational risks and potential safety risks, which we've gone through today. But the big key takeaway is by understanding your power quality on your network, you can understand how to mitigate the exposure to these risks and reduce the impacts towards your business. So hopefully it's been quite insightful from that side, if not just giving you a deeper dive into some of the things you maybe know a little bit of. The next thing we're going to look at on the next session is going to be the hazards and risks around substation entry or electrical switch rooms, how to identify the right PPE, and then how to marry up those labels and what they mean. So a bit of a dive into the PPE and the requirements around interpreting that data. So yeah, just while I spawned as well, just to finish before we go to the Q&A, we have just been looking at venues for our 2026 UK event, which is going to be in London in June. The dates will be announced and the formal venue will be announced in the next 2 weeks. But just to give everyone a heads up, if anybody's interested in attending or potentially getting involved, let us know in the Q&A or in the poll afterwards, just to let us know what you'd be how you'd like to get involved in that. But now, yeah, Ben, is it okay if we just look to the Q&A and see if we've got any questions that we can hopefully answer with Steve and Tony's experience?
Yeah, of course. If anyone's got any further questions, please do drop them in the chat or in the Q&A. I'll start with this one, Dan. So this is from Dave. Computer servers and UPSs are considered capacitive loads. Is that correct?
Yeah, they can be. The electronic loads like that are going to have generally a very good power factor, so either slightly inductive or slightly capacitive. But if in the context of power factor correction, if you had a whole building full of computers, you probably wouldn't have to do a whole lot of correcting. UPSs sometimes they're interesting. In some cases, they have input harmonic filters, and at low load levels, there have been problems that I've been aware of loads kind of going more capacitive, and that can cause problems with standby generation. We had one data center, kind of locally here in Central Texas, that every time they went and did their, kind of their monthly load test, the transformer, or they'd switch the UPSs over, generator would shut down because of overvoltage because it couldn't deal with the capacitive load. They had to change make some modifications on the UPS to drop off some of that filtering at low load levels to not overcorrect during those times.
Yeah, there tend to be anything over a 0.96 leading power factor, and the generator's ability to provide power just falls off a cliff.
One of the biggest things as well to consider, especially I think Steve touched on it, especially around the loading, transformer loading. So again, a lot of people, you've got your original design, but we don't often say like that. We often modify, enhance, whether it's a downstream equipment in terms of like server racks or production equipment, whatever we're doing, we often modify what's on the end of the transformers in terms of load, variant types of load, and often it's not normally done by many M&E companies in current. So it's how many amps is the load, and then they'll base that upon the kVA of the transformer. So one of the big things that I see often is that communication piece where things will get added on, 50 amps here, 100 amps there. And often most networks, we build them with redundancy. So we normally have two transformers feeding one low voltage board with a bus coupler open, normally with the capability of one transformer being able to feed the whole LV board for the events of maintenance or faults on one side or the other. And so I'll often see is not taking account nonlinear load, and then we'll overload each transformer by adding nonlinear load on, where then we no longer have that n+1 arrangement. So effectively, we've now lost our reliability and redundancy in the network by just adding on these loads without taking into account the power quality characteristics. I think it's quite a big thing that I see often, and it's such a big impact.
It is a good example of that from a hospital that repurposed one of their transformers purely for MRI scanners, which are very noisy from a harmonic point of view. And long story short, that transformer was loaded at less than 30%, but in actual fact, when we did the analysis, it was loaded just over 100% of its capacity because the harmonic loss factor was 12. And if you can picture that curve, way past our example of 7, the transformer's ability to deliver that power had massively diminished, and as a result, the voltage distortion had gone up to an unacceptably high level, which in hospitals for some equipment is actually only 3%.
That's perfect. Have we got any?
Dan, one observation. Several of your comments have been around systems where things have changed, right? And after the change, things don't work nearly as well as they did at the beginning. And I think that's an important lesson to take away from all this, that the power system, sometimes we think of it as, well, it's just there, it's delivering power, it's a static thing. It's really not, right? If you're introducing new types of loads, you're introducing additional load, you have to consider not just like the total loading level, or do I have physical space to put in a new circuit breaker to feed this thing? What about harmonics? What about the sensitivity of the loads that are going in and how that may be compatible or not with existing processes? It's hopefully, if nothing else, this gives you, all of you who are listening, some ideas of things to consider when you're looking at making those kind of changes.
Yeah,
good point.
Definitely. Were there any other questions there, Ben?
No, I think we can call it a day there, Dan. If anyone's got any further info, they've got the details on the screen. So
yeah, perfect. No, well, thanks very much for joining. Look forward to seeing you at the next one. If you do want the recording, obviously let us know. We can get that through to you. But if you're registered, you'll get it anyway. But yeah, thanks very much, everyone.
Thank you.
thank you, everyone.